Okay, welcome back to the lecture series on levers and mechanical advantage. It's advised that you guys are again fairly familiar with the concepts of torques. Good knowledge on the understanding of rotational forces is going to be quite important for your understanding of levers and mechanical advantage. So let's start off with the definition of a lever. So a lever is a bar, or any bar, or some rigid structure that is hinged at one point and to which forces are applied at two other points. So this has significant application to the study of biomechanics and human movement, given that bones are the rigid structures that are hinged at a point, in other words your joint, and to which forces such as gravitational force, muscular force, or external forces are applied at other points along that rigid structure. So by understanding what these forces are and how they tend to act on the different structures and the different types of joints that we have will help us understand whether certain joints are geared more specifically to the generation of force, stability, or speed. Okay, so how do we unpack this? If I had some kind of a rigid lever, let me actually just use a slightly different color here. If I had some kind of a lever system, or just a bar that is on some kind of a fulcrum or axis of rotation. So your fulcrum is the point about which a bar tends to rotate. And I have a force that I tend to apply at some given distance. So let's say, for example, I have a force that I'm applying here. We'll just call that F. This will tend to cause rotation of this rigid bar about this axis, right? So we can tell that this would kind of cause a clockwise rotation. How good this force is at creating this clockwise rotation is also dependent on where along this bar that force is applied. So I have to factor something else in, which is the distance from the axis of rotation. We'll just call that A. Right? Say that there's another force acting on the opposite end that we'll just call R, just to denote a resistance force. It will tend to cause a counterclockwise rotation. Again, how effective this particular force is at creating this counterclockwise rotation is dependent on how far it is from the axis of rotation, and we'll call that length B. Right? So there's a torque created by this force R, which is equal to the magnitude of R multiplied by its distance from the axis of rotation, which is that length B. In a similar manner, this torque created by the force F is equal to the magnitude of the force F multiplied by the distance that it is from the axis of rotation, which is just called A. So in equilibrium situations whereby there's no net rotation, we know the following to be true, right? We know that the sum of all torques or moments is equal to 0, right? There's no net movement, which in essence then means that the force applied by me multiplied by the distance at which I apply that force from the axis of rotation is going to be equal to the resistance force. Sorry, wrong color. The resistance force multiplied by its distance from the axis of rotation. And from this relatively simple formula, I can create a set of ratios, which looks something like the following. If I take force and divide it by this side, then I will have R, the ratio of the resistance force, divided by F, right, is going to be equal to A divided by B. Okay, so in essence there are a couple of things that I just want to unpack over here. So this is the resistance force, or we can call that the load, right? This over here is the effort, or in essence, if you want to think of it as a muscular force, that wouldn't be entirely incorrect. So we're looking at the ratio of resistance to effort, or load relative to effort. A is the distance that the force is from the axis of rotation, which is called your force moment arm. And B over here is the distance that the resistance is from the axis of rotation. So it's called your resistance moment arm. Okay. And the ratio of this force moment arm to resistance moment arm is called your mechanical advantage of the system. So either there is mechanical advantage present, or there isn't, or it is indifferent. In other words, if the length of A is equal to the length of B, we just get a value of 1 over here, meaning it's neither advantageous or disadvantageous. But there's a couple of things that we can kind of get from this particular ratio. Say, for example, that I were to, instead of applying the force at the very end here, I apply the force over here, right? That now, instead of my length A being this particular length, A has become shorter, right? So now A is less. So A, the value of A has decreased over here. We can tell that A would be significantly less than the length of B, meaning that this particular ratio would now be less than 1, right? The ratio of R over F is less than 1.0. If you don't believe me, let's say, for example, that A was a value of 1, this was 1 meter, and B was a value of 2 meters. Well, 1 divided by 2 is 0.5, that's less than 1. Okay. If the value is less than 1, then it's a disadvantage. The reason being is that if A is so small, in order for me to maintain equilibrium here, F has to increase drastically, right? So when A becomes smaller, F has to become larger in order to keep this whole system in equilibrium. Okay, so hopefully that makes sense. Vice versa, if I were to make A longer or B shorter, let me just try and use again a different color over here. Let's go with let's actually go with red. Let's say, for example, I had to apply R a distance over here. Now all of a sudden B becomes shorter, right? So if B decreases, then R has to increase, right? So again, if I look at this specific ratio over here, in this instance, I would sit with a value greater than 1, which would give me an advantage in terms of the amount of force that I have to apply. So say, for example, now the ratios were flipped. So say, for example, A now is 2 meters and B is 1 meter. Then I have a number 2. I have a value of 2 over here, which gives me a mechanical advantage. It basically means for this whole system to be in equilibrium, that the force that I have to apply can also decrease. So if R does not increase, right, then F that I apply over here can decrease, and this whole system would still be true. Okay, so again, this is looking at the ratio of load versus effort, or resistance versus force applied. Okay. Again, if A is equal to B, then this whole system is equal to 1, or the ratio of R over F is going to be equal to 1, which is then neither an advantage or a disadvantage, right? And this type of a system, this type of a lever system, is called a type 1 lever. And basically, with a type 1 lever, the following has to be true. There is obviously a rigid bar. The fulcrum is always in the middle, and the force and resistance are on either side of the fulcrum. Right? It does not matter where the force is applied or where the resistance is applied. It can be any distance as long as it's on either side of this fulcrum. Force is on the one side, resistance is on the other side. It can be in any direction and it can be any distance. It doesn't really matter as long as it's on either side of the fulcrum. So hopefully that makes sense. Alright. So there are different types of levers that we can get. The second is a type 2 lever. It's also called a wheelbarrow lever. In this system, again, we have a rigid bar. We have a fulcrum, that's always true. But in this type of a scenario, both the resistance arm and the force arm are on one side of the fulcrum, right? We still have our lengths B and our lengths A to denote the distances that each of these is from the axis of rotation. Remember, this over here is my fulcrum, the point about which we tend to rotate. Note again how this is similar, I guess, in many ways to a wheelbarrow. So here we have some kind of resistance and the force that I tend to apply. Notice again that if I look at my ratio of R over F, which is equal to A over B, notice that A is significantly greater than B. So it's like we said, that when A increases, the force that I have to apply tends to decrease, right? Or it also can mean that for a given force, there's more resistance that I'll be able to lift, right? So again, in this case, the value of the ratio is going to be greater than 1, which is going to definitely give me a mechanical advantage. Again, the forces and resistance arms can be shifted, but both of them are on either side of the fulcrum, and the force moment arm is always larger than the resistance moment arm. And then I also have a type 3 lever, which in essence is most of the joints in the human body. Again, I'll have a rigid bar. Again, the fulcrum will be on one side, so that's my fulcrum. But a substantial difference here is that the force arm and resistance arm are on either side. But in this case, the length of A is going to be less than the length of B. Right? So again, if I look at my ratio of load versus effort, which is equal to the length of A relative to the length of B. Again, over here, when B increases, that means the force that I have to apply will also increase, or the resistance would have to decrease in order to maintain equilibrium. In this case, the ratio will always be less than 1 because A is substantially less than B, or B is greater than A. So when that happens, this ratio will be less than 1, which is really quite silly because it's going to give me a bit of a disadvantage, right? You can think of this as being your arm, your forearm, right? So say, for example, I have an arm that's hinged at the elbow joint. My muscle is going to be quite close, and here's a weight that I'm carrying, which is the resistance. it means that I have to exert quite a large muscular force to overcome this external resistance that I'm holding, right? But something that is of interest with all these different types of joints is the relationship between speed of movement versus strength, right? In scenarios whereby something tends to favor strength, it would have to be this type of a type 2 lever setup, whereby the force moment arm is greater than the resistance moment arm. It tends to favor the production of force over here, or I have to exert very little force in order to move a given resistance, right? It's a fairly good system that tends to favor speed. But also notice that when the force arm is so large, that as this tends to rotate to some kind of a new position over here, that there's quite a large amount of displacement that has to occur, and you'll notice that the end over here is very, very small. The displacement on this side is going to be quite small. In this scenario, it's quite different, right? Notice that if I have displacement that tends to happen here, I have to exert quite a little bit of force in order to displace this rigid lever from position A to position B over here, but the end point tends to move quite dramatically, right? So the displacement from here, let's call this point 1 to point 2, is going to be much greater than this point 1 dash to this point 2 dash. Okay, so force production that's closer to the axis of rotation requires very little force in order to move something a much greater distance. Okay, so type 3 levers tend to favor the production of speed, whereas type 2 levers tend to favor the production of strength. Type 1 can go either way, and the reason that is the case is it depends on ratio of A over B. So when A is greater than B, it favors the production of strength, and when A is less than B, it tends to favor the production of speed, right? Speed of movement is going to be greater for those very reasons. So that's a very brief introduction into the concepts of levers and what their typical applications are. Be sure that you can identify the different types of levers, so from type 1, 2, and 3, and what differentiates them. Also be able to explain concepts of mechanical advantage and why that would be the case by linking specifically to these ratios over here, and what effect a change in any given length has on the mechanical advantage of the system. So hopefully that has made some sense. Remember, you need to couple all of this with your textbook, with the slides and with the manual, in order to get a holistic understanding of it. That's it from my side. I'll see you guys next time.